In this segment of Security Plus 501, we're looking at Objective 6.2, and it states we are to explain cryptography algorithms and their basic characteristics. And in this particular area, we're looking at specific algorithms such as MD5, SHA variations, HMAC, and RIPE-MD. Now, hashing algorithms are, just to let you know if you haven't already discovered this with your other videos and reading, are mathematical functions that are there basically to be used and create a message digest, or sometimes the references a hash code from variable types and lengths of input. Now, there's a limit to the size of a message output that a hashing algorithm can process before the hash code is considered no longer secure. The hash code uniquely identifies data input and should be used to protect the message integrity, where it makes it very difficult to find a different data input that produces that same hash code or output. And the first one here we're looking at here, MD5. MD5 stands for Message Digest 5. There's different or previous versions of that. It produces a 128-bit message digest, and in today's standards, it's really considered too small and is prone to what they call collisions. And collision is basically where you have two different inputs that produce the same output or the same digest. Now, I'm using these words such as output and digest. Like I said, you may have other books or other videos, they may reference a different word or term for that. Some common ones when they say digest may be output, checksum, or fingerprint. And all that's saying is that whatever the input is, it's going to produce, and in hashing algorithms, a digit form of a hexadecimal output. For example, this is a test. If I was to use MD5 to hash it, this would be its output or its digest. Now, all inputs, we could have a large amount of different types of input. That's infinite, as they say. But each hashing algorithm has a finite possibility or finite output. So each one, in its own way, it does have a limitation of how far it could go. So what makes one hashing algorithm stronger than the other is the digest size. So like I said, MD5 with 128-bit is, in today's standard, too small as far as like some of the possibilities. But MD5 can still be found utilized in certain areas. Secure Hash Algorithm, or SHA, and it was modeled after MD5. It was there basically to replace it. Even though SHA is there to replace MD5, SHA in itself, especially SHA-1, is considered strong of the two, but they have other renditions such as SHA-1, SHA-2, and SHA-3. SHA-2 has different flavors, as I like to call it, based on the digest value or the output. So for example, of SHA-2, it may have different variations such as SHA-256, 384, and 512. All those are versions of SHA-2, but they differ by the naming convention and the size of their hash values. Like I was saying before, SHA-1 is basically being phased out due to weaknesses, and it's prone to collision attacks. SHA-3 is as strong as SHA-512, the SHA-2 rendition, but is considered by NIST, which stands for National Institute of Standards and Technology. SHA-3 is basically considered the next generation tool for securing the integrity of electronic information, and is considered as a backup, basically, of a SHA-2 when and if it does start displaying levels of weakness. So all three of these can still be found being utilized. SHA-3 being the newest, it's now starting to be seen and utilized, but not as prominent as a SHA-2 hashing algorithm. Now, HMAC, which stands for Hash-Based Message Authentication Code, provides message integrity because it does integrate hashes, and in particular it uses hashes that we're looking at here and what we talk about, such as MD5 or SHA-1. So it's providing integrity, but HMAC also provides authentication. It's providing authentication because now, along with the hash, it's providing a secret cryptographic key, a symmetric key with the message before it's actually being hashed. And like I said, it's doing that with MD5 or SHA-1. And then it provides a server, for example, and a client. If they were communicating with a secret key known only to them, they establish a handshake. The client combines that secret key with a message, which is then hashed to generate the digest. The client then sends the message to the server, but as it's doing it, it's not sending the secret key. It's sending the message back to the server, and the server combines and agreed upon key with that handshake with a message which is then put through the hashing algorithm to generate that output or the digest. Now, when that receiving component, the server in this case, looks at the two digests, they should be the same when they are compared. And once again, that'll be able to provide the integrity side. So they do establish a secret handshake between the two. It does combine that secret symmetric key along with the crypto hash function, but the secret key is never actually being sent. So we find HMAC utilized in certain areas that you may have already covered, such as within IPsec, secure web with SSL, TLS versions, SSH, the tunneling mechanism, newer versions of NTLM, in particular version 2. We find it also in PGP, where they're providing some sort of password strength or lengthening or stretching. We find it also on PBKDF2, and also some of the newer ones, such as to secure your VoIP environments, those particular protocols, called Secure Real-Time Transfer Protocol. And also, we find it being utilized within your one-time passwords or OTPs. And the last one we'll be looking at here is RIPEMD, which stands for RACE, sort of kind of an acronym within an acronym. RACE is, I'm highlighting the first letters in each part of the word, Research and Development in Advanced Communication Technologies in Europe, European Standard, Integrity, Primitives, Evaluation, Message Digest. That's a very long and crazy and confusing acronym. RIPEMD. So RIPEMD is founded upon the obsolete MD4 hashing algorithm, but it also provides increased security. Different versions of it too is offered, as well as the digest size. So they may have, for example, RIPEMD 128, 160, 256, and 320. The naming conventions will be based off that digest size. RIPEMD 256 and 320 are less likely to produce the same output based off the size of their digest, which makes them more commonly utilized. So the 256 and 320 less likely to produce that same output on different data inputs because the digest is larger. But beyond that, they don't really offer any stronger security. But 160, RIPEMD 160 is most commonly, and when they compare the SHA-1, it has fewer security issues than that. So both of those are still being utilized. You can find all these different hashing algorithms. But these are 4 commonly found hashing algorithms in or within the world of information security. And they provide a critical component in protecting data output from being seen by unauthorized parties.